So I'm going to talk to you about 4 different aspects of the synthesis that I've done. And yeah, we're going to take a very synthetic look at what I've achieved over the years with some interesting bits of science. Okay, so we're going to start with some lithium nitride. So this was work I did at University Nottingham back at the beginning of the millennium, and then moved to Glasgow after my undergrad. But we were interested in making lithium nitride nanofibers. So simultaneously, this is one of my favorite syntheses, but also at the same time, my most dreaded and most hateful synthesis. And hopefully you'll see why. So first of all, we have to make some lithium nitride in its purest possible form, which involves a vacuum glove box filled with argon. So we evacuate off this glove box overnight and then refill it with argon. We can clean the atmosphere within that box down to about 2 parts per million of water and oxygen by using a sacrificial pool of sodium. So this basically involves a large bowl of liquid sodium where you're scraping the top to get rid of the slag that forms on the top as it pulls all the oxygen and water out of the atmosphere. So you imagine this, you're in this glove box, your arms are stuck, it's about 50 degrees centigrade, your sweat pouring down your face, trying to do this whilst you're polishing pure metallic lithium until it shines inside the glove box and then putting it into this reactor vessel. So you put the lithium into more liquid sodium, seal the whole thing up, and then heat this out of a glove box for a good number of hours, if not a few days, under a nitrogen atmosphere. The lithium reacts with the nitrogen to form lithium nitride. The liquid sodium keeps the atmosphere nice and clean and gets rid of any oxygen contamination. And then finally, you can use the cold finger here to distill off the sodium. It's a great experiment, great fun if you like liquid metals, but an absolute pain to do. Anyway, once you have your purple crystals of lithium nitride, you can put them into a iron foil liner. Inside yet another pot. Under massive vacuum, you can heat them up with a temperature gradient, and you can do a chemical vapor transport reaction to actually move the nanofibers and form nanofibers on the nichrome wire throughout the temperature gradient. Really interesting synthesis to get some nanofibers. We can see we get fibers and wires with quite a high aspect ratio. We get ribbons and other nanostructures as well. Electron diffraction here shows that we've actually got lithium nitride in the middle, surrounded by a shell of lithium hydroxide. These actually have very interesting applications in hydrogen storage. So for instance, these things will take up about 11.5 weight% of hydrogen, which is pretty significant. And if you start intercalating different materials like carbon and molybdenum and cobalt into the ends of these fibers, you can actually form nano batteries with the lithium nitride. So there's lots and lots of potential there. Really interesting stuff with some complex syntheses. All this work was done about 15 years ago, and we have only just managed to actually get it published, but it went into Nature Communications this year. So a nice impactful journal there. Okay, so moving on to the second system, which was more about my PhD work at University of Glasgow. We were interested in chalcogenide structures and looking at the different syntheses of these. So we've got a quartz ampule synthesis here, where we actually use glass blowing techniques to seal quartz ampules. We can put elemental powders in one end. We can do a surface assisted synthesis with some tantalum foil in the other end, and this little neck that we've blown into the glass prevents the two from actually mixing. If we use a 1:2 ratio of elemental powders, we can actually form the tantalum disulfide. If we use a 1:3, we can use tantalum trisulfide. If we change the heating arrangements, we can actually get ribbons versus particles versus wires. And we can actually control the not only the morphology, but we can also control the actual structure of the tantalum and the sulfides. Okay, and the nanofibers are simply just removed with a pair of tweezers. Okay, so looking at some of the characterization, we've got the different morphologies with their EDX showing it's approximately 1 to 2. We've got our wires and ribbons. We've got electron diffraction to show us what we've got. And XRD actually shows us that we can get the 1T, the 2H, the 3R polytype structure for the tantalum disulfide. So the difference between the different polytype structures is due to both the coordination of the tantalum atoms with respect to the sulfur atoms within the tri-layer sandwiches, and indeed the alignment of the sandwiches themselves. We can use the specific heating regimes to actually isolate any of these three structures, and the 1T actually shows superconductivity down at very low temperatures. And again, that gave us a few interesting publications, one of which was an Angevant paper showing the syntheses. What really gets quite interesting is when you start moving to TaS3, we're then in a position to form nanofibers of this very interesting one-dimensional material. So what's really interesting about tantalum trisulfide is that we have these chains of green atoms that run through the structure, and they are the tantalum atoms. So we can actually look at making nanofibers that are effectively self-insulating wires with the tantalum atoms running down the lengths of the wires with the sulfurs around them on the side. Being able to take electron diffraction patterns down the actual length of a nanofiber was quite an interesting challenge. So very briefly, we're able to actually encapsulate these nanowires into epoxy resins. You can align the fibers down with a silicon wafer. You can put them into a little holder for the TEM. You chop the top off and the bottom off, and then you grind away until you have a vertical alignment of nanofibers in this middle section here. That's actually so thin that it's electron transparent. And that way you can actually get electron diffraction patterns down the actual lengths of these nanofibers. So that was quite interesting. Moving on to some titanium oxide work. And this was 6 years of my life at UCL, working first as a postdoctoral researcher and then as a Ramsey Fellow. We were interested in self-cleaning materials. So titanium oxide is a standard self-cleaning material and used in self-cleaning windows. So it's an advanced material there. What we wanted to do was to nitrogen dope in order to get a self-cleaning material that works indoors. So what's this all about? It's all about healthcare-associated infections. So this work was carried out back in 2008. Hence, the data on this slide is slightly out of date. But there was a huge number of people who suffered from healthcare-associated infections and a massive cost to the NHS in the UK. The numbers in America were significantly higher, and indeed today the numbers are significantly higher again. So let me introduce you to two of our little friends that you're probably aware of. At the top here we have E. coli, and at the bottom here we have MRSA. So these two bacteria are actually very, very common. Every single one of us sat looking at this presentation actually has E. coli already in our guts. And I would say 60% of the population has MRSA up your nasal passage all the time. And these bacteria are actually not a problem most of the time. However, when you transfer them to patients who have immunosuppressancy, they can cause really significant issues. So in hospitals, it's all about hand-touch surfaces. Keyboards are absolutely disgusting if they are in a communal area. Loo flush handles and railings for stairs and such are some simple and easy ways that we can actually make self-cleaning surfaces indoors that can kill the bacteria, or at least won't harvest the bacteria on them. So how do we do it? Well, we look at some atmospheric pressure chemical vapor deposition. So this is my rig from UCL. You can see at the back, we've got chambers of liquid chemicals and volatile chemicals that we can heat up, changing the vapor pressure. We can pass heated gas through them. We can take all the 4 different feeds down here and onto a heated glass substrate. So we can do chemical vapor deposition down onto the glass. This is an example here where we've actually got nitrogen doped TiO2 films. The synthesis is carried out at 500 degrees centigrade using tickel and ethyl acetate to give us our titanium oxide. And then we have T-butyl amine to give ammonious formation in situ. What we found here that was actually really quite interesting is that when you dope with titania with nitrogen, you have 2 different options. You can put the nitrogen in exchange of a oxygen, which is a substitutional doping, or you can add it to the interstitial sites within the crystal structure. XPS here is a fantastic technique, as we have heard about today from Mark. But XPS here is actually really useful because we can tell the difference between interstitial and substitutional. It is, however, very, very difficult to make samples that have only one form, whether it be interstitial or substitutional. The green sample in the middle is what normally occurs where you have both. There was a raging argument in the community as to whether it was substitutional that was best or whether it was interstitial that was best, and we were the first ones really to be able to make samples that had only substitutional and only interstitial, as well as samples that had both. And we really showed that the interstitial was the one that really made the difference in terms of the photocatalysis. So that was an interesting piece of work, and then we went on to show sulfur doped and various different types of solid state chemistry with CVD, Sol gel, all looking at hospital acquired infection control. That then developed into some Janus particle work. So Janus is the Roman god of new beginnings and transitions. And is depicted by a 2-faced coin. So we're looking at nanoparticles that actually have 2 different sets of properties on 2 different faces of the same particle. And the reason we're trying to do this is my favorite equation in the whole wide world, which is water plus green energy goes to hydrogen and oxygen. So this is the equation that actually drives vast amounts of my research all over the place. And is obvious in terms of the future economy of the energy landscape. So what we're interested in here is really a nanoparticle that contains a hydrogen catalyst uniquely bound to an oxygen catalyst as the same particle. And the idea here is that you can put light directly in and you can yield hydrogen and oxygen from the particles. So a very, very quick sidestep into some semiconductor photo-physics to show how this works. Using band theory, you can take the electrons in a solid state structure. You can look at the highest occupied band, which is your valence band, your lowest unoccupied band, which is your conduction band, and a band gap between them in a semiconductor. We take a photon in, promote an electron, which of course leaves a hole in the bottom. And this allows us to do reduction chemistry with that electron and oxidation chemistry with the hole that's been left behind. So we kind of get two for one out of a single photon. The problem, however, is this recombination where the electron simply can drop back down from the conduction band back into the valence band and wastes all of the energy. So a solution to this is to align 2 different semiconductors with aligned band gaps, and we can then put 2 photons in. We can take an electron from the valence band here into the conduction band. It can drop down into the hole created when the other electron went up. So this electron is prevented from dropping down. This electron is prevented from dropping down. And we can actually have this Z scheme. So that's really where I'm going to with my Janus particles. So let's have a look at some syntheses. So we want to take a soluble substrate. We're going to coat it using our surface coating techniques to give layer 1. We're then going to apply layer 2 on top of that, and then we are going to be able to remove the substrate to leave our Janus particle because they should fracture vertically rather than delaminate. So a nice example here is to take some titanium oxide as mixed phases. So we take a sodium chloride substrate at with a melting point of 800 degrees. We can do a simple sol gel synthesis, which gives us TiO2. And if we anneal that at 700 degrees, we end up with the rutile phase. If we then apply Anatase on top by doing the same sol gel synthesis, but this time at 500 degrees and not holding it for too long, we end up with these Janus particles. And note that these are actually very different from core shell particles, where one phase is completely encased by the other. Both of these phases are freely accessible to both the light and the water. We did a synthesis like this where we got 5 layers of rutile followed by 5 layers of Anatase, and it yielded a nice film that we could flip over. So this is Raman spectroscopy, where we can see on the top side we have a very good match for Anatase, and on the bottom side we have a very good match for the rutile. So that shows you how the synthesis works. Interestingly, with this, what I managed to do was I managed to get a number of samples where we had 8 layers of Anatase, 2 layers of rutile, 5 layers of each, followed by 5 layers of rutile and 2 layers of Anatase. And the power of XPS, which Mark has already told us all about, the amazing XPS, allowed us to do some very clever stuff. And this solved another of the big arguments in the scientific community. So there was an argument between the computational chemists and the experimental chemists as to what happens in a mixed phase TiO2 system. Everybody knew that adding Anatase to rutile made a better photocatalyst, but it was really quite hard to explain. So there's 3 possibilities when you align the band gaps of these 3 systems, thinking back to my circular diagrams earlier. So you can align the valence band and you see that you've got a 3.2 versus a 3 for Anatase and rutile. You can have a raised Anatase or you can have a lowered Anatase. And the computational guys all said it was a lowered Anatase. The experimentalists all said it was a raised Anatase, until we came along with our samples that actually showed that it is indeed a lowered Anatase. And this is actually really quite important because in the combined synthesis of Anatase and rutile, it's quite important which one is the oxygen catalyst and which one is the hydrogen catalyst, or at least which one is the oxidizer and which one is the reductant. So that answered quite an interesting question, and got us a paper in Nature Materials, led by Scanlon, who did the computational work for this. But that ended up with, I think that's now had 1,700 citations since 2013. So it's actually a really quite a nice paper there. So this work moves on. We can now look at Janus-like particles. So rather than just having titanium, we can actually start mixing various phases. So we can dope individual sides. We can start putting nanoparticle islands on the top and bottom. And we can start picking hydrogen and oxygen catalysts to go with it. So these red samples here are, of course, tantalum nitride, which is a beautiful material, but you can actually have that on top of vanadium oxide. We've done work, as you'll see in a minute, with bismuth vanadate and cadmium sulfide. We've done work with tungsten oxides in various forms and bismuth vanadates. Iron oxide composites and copper oxide composites are, of course, really, really interesting, as we've just heard from Adam as well. So the synthesis itself has huge amounts of potential to really give you a lot of power. So very, very briefly, this is the bismuth vanadate cadmium sulfide. We can actually put this onto an aluminium substrate. We can use electrophoresis and sol gel in order to get our samples. And of course, we can end up with our bismuth vanadate cadmium sulfide Janus particles with the Z-gate system here set up. So we can take in 2 visible light photons and we can actually split water with that using the experimental setup and gas chromatography. So that really is a whistle-stop tour through four of the interesting syntheses that I've been involved with over my career. It spans across from Nottingham to Glasgow to UCL and now, of course, to Swansea as well. There are far too many people to name individually, but many of them I'm very, very grateful for.